Hello friends, so today we are going to solve the question from Heat and Thermodynamics, and these questions are from the year 1988. One question, 1989, two questions, and 1990, one question. So in totality we are going to solve 4 questions. So first question, it was asked in the year 1988, and it states that 2 moles of helium gas with gamma equal to 5 by 3 are initially at a temperature of 27 degrees centigrade, occupy a volume of 20 liters. The gas is first expanded at constant pressure until volume is doubled. Then it undergoes an adiabatic change until the temperature returns to its initial value. So based on this, we are having 3 questions. Part A, sketch the process on a PV diagram. What are the final volume and pressure of the gas? And part C, what is the work done by the gas? So first of all, we have to plot our PV diagram. Okay. And so PV diagram is, this is our volume on x-axis and pressure along our y-axis, and it states that initially it is a temperature 27 and volume is 20 liters. Okay. So let us suppose this is the volume and it is our 20 liters. So it will be 20 into 10 to the power minus 3. Okay. And at a certain pressure, let us suppose that pressure is our P1. Okay. So this will be over, this volume is, let us suppose we call this as V1. So this comes as P1 V1, and let us assume that temperature is our T1. Then it is compressed at a constant volume, constant pressure, and the volume becomes doubled. So for constant pressure, we can just extend it, and the volume becomes double. So this will be our double, that is 40 into 10 to the power minus 3. Let us call this as V2. Okay. And no doubt the pressure will be same, but to make a slight differentiation, we are going to call this pressure as P2, volume as V2, and temperature as T2. Okay. Pressure will be same, P1 is equal to P2, but only to differentiate. And let us suppose we call this as point A and this is point B, and then it is an adiabatic process, and okay, so adiabatic process, let us suppose it something like this, and this is point C, and this is point C. Let us assume that pressure is our P3, volume is V3, and temperature is our T3. Okay. This is our basic PV diagram. So from this figure we can clearly see that our AB is our isobaric process. AB is our isobaric process. Okay, and B to C is our adiabatic process. B to C is our adiabatic process. Now we come, this was part A, now we come to the part B. In part B, we have to find out the final volume and pressure of the gas. Okay, so it means we start with our final volume, that is our V3. So under initial condition, number of moles, that is N, it is given as 2 moles. T1 is given as 27 degrees centigrade, so this will be our 300 Kelvin, and volume V1 is given as 20 liters, so 20 into 10 to minus 3, and gamma, that is adiabatic ratio, is our 5/3. And after isobaric process, volume is double, so we can say our V2 is equal to twice of V1. This comes as our 40 into 10 to the minus 3, and our, we can find out the temperature. For, we can use ideal gas equation, which is equal to PV is equal to nRT, and our pressure is constant. Therefore, we can write this equation as T2 by T1 is equal to V2 by V1. So we get this as T2 by V2 by V1 is equal to 2, because the relationship is twice, and therefore we get our T2 is equal to twice of 300, giving us 600 Kelvin. Okay. And from B to C, it is adiabatic process. So B to C, the process is adiabatic, and it is mentioned in the question that it returns to the original temperature, that is our T3 will be once again is equal to T2, which is our 300 Kelvin. Okay. And here we can use the relationship that TV gamma minus 1 is equal to constant. So which basically means that T2 V2 gamma minus 1 is equal to T3 V3 gamma minus 1, and gamma is our 5/3, so gamma minus 1 will be equal to 2/3. So we get that our V2 T3 is our 300 Kelvin, And okay, so we can write that our V3 raised to power 2 by 3 will be equal to our 600 divided by 300 and multiply by V2 2 by 3, and this 600 goes by 2, so we get this as twice V2 2 by 3. Okay. And from here we can see that our V3 will be equal to, this comes as our 2 root 2 times V2, and V2 we already know is our 40 into 10 to the power minus 3, so we get that our V3 will be equal to 2 root 2 into 40, this comes as 80 root 2 liters. Okay. And let's substitute the value of root 2 also, it's more easier to, root 2 is 1.414, so this gives us that our V3 will be equal to 113.14 liters. So this is our final volume. Now we come to the final pressure. So final pressure, first of all we are going to find out our P1 by using our ideal gas equation. So we can say our ideal gas law, it gives us that our P1 V1 is equal to nRT1. This gives us that our P1 is equal to nRT1 divided by V1, and we can write, substituting the value of N is our 2 and R is our 8.314, temperature is our 300, and V1 in liters we can write this as 2 into 10 to the power minus 3. So from here we get our P1 is equal to 2.494 into 10 to the power 5 pascals. Now from A to B it is isobaric, therefore the pressure is same. So from here we can say that our A to B isobaric, therefore we can say our P2 is equal to P1 is equal to 2.494 into 10 to the power 5 pascals. Now we come to from B to C, and from B to C it is adiabatic. And for adiabatic we know that PV raised to power gamma is equal to constant, or from here we can say that our P2V2 gamma is equal to P3V3 gamma, and we are required to find P3, therefore we can say our P3 is equal to our P2, and this comes as our V2 upon V3 whole raised to power gamma, and we already know the ratio is our V2 by V1. एक second. Yeah, we know our V3 and we also know our V2. Okay, so we can say that our this will be equal to P2 is our, this we can write 1 upon 2 root 2 whole raised to power gamma, and gamma in this case is our 2 by 3, 5 by 3. Gamma is 5 by 3. Okay. So therefore we can write that our P3 is equal to P2 times, and this can be written as our 1 upon 4 square root of 2. Okay. And P2 is our, we already know this value, that is our 2.494 into 10 raised to power 5 divided by, and this comes as 4 into 1.414. So therefore we can say that our P3 will be approximately equal to, this will be our 4.41 into 10 raised to power 4 pascals. So we got our final pressure as well as the final volume. Now we come to the part C, that is our work done. Part C, work done by the gas. And here we are having two processes. One second. Sorry, it is isobaric, not acyclic. Because it is a constant pressure. Okay. So here we are having two processes, isobaric and adiabatic. So total work done will be the summation of both. So we start with our isobaric. Isobaric process, we know that the work done, let us call this as our W isobaric, Wi will be equal to P1, and this comes as our V2 minus V1, and this can be written as NR T2 minus T1, okay, because pressure is our constant. Therefore we can say that work done under isobaric will be equal to, we can write this as 2 into R is our 8.314, and this comes as our 600 minus 300, which gives us 4988.4 joules. Now we come to our adiabatic process. Adiabatic process, let us call this as W adiabatic. Okay. And the work done is according to our first law of thermodynamics, as is the adiabatic process, the value of Q is equal to 0. Therefore WA will be equal to negative of our U, that is change in internal energy. And we know that this is change in internal energy is equal to N CV T3 minus T2. and value of n is our 2, and this is our 3 by 2 times r. R is our 8.314, and we get this as our 300 minus 600. Therefore, we get our delta U will be equal to minus 7482.6 joules. From here we can say that our work done because of adiabatic will be equal to, which is our negative of U, this will be coming as plus 7482.6 joules. Now we can just total work done is equal to respective addition. So we can say our total work done, that is our W, is equal to work done because of isobaric plus work done because of adiabatic, and we substitute the value where W is equal to 4988.4 plus 7482.6. This is approximately equal to 12471 joules. So these were the three sub-questions for the first main question. Second question, it was asked in the year 1989, and it states that an ideal monatomic gas is confined in a cylinder by a spring-loaded piston of cross-section 8 into 10 to the minus 3 meter square. Initially, the gas is at 300 Kelvin and occupies a volume of 2.4 into 10 to the minus 3 meter cube. The spring is in its relaxed, unstretched and uncompressed state. The gas is heated by a small electric heater until the piston moves out slowly by 0.1 meter. Calculate the final temperature of the gas and the heat supplied in joules by the heater. The force constant of the spring is 8000 Newton per meter, and the atmospheric pressure is 2.5 into 10 to the power 5 Newton per meter square. The cylinder and the piston are thermally insulated. The piston is massless and there is no friction between the piston and the cylinder. Neglect heat loss through the lead wires of the heater. The heat capacity of the heater coil is negligible. Assume the spring to be massless. Okay. So basic figure is given to us. We have a spring which is connected to a rigid support, and this is our movable piston. So as the heater is going to supply heat to the gas, the piston is said to be moved by a distance of 0.1 meter. So obviously the spring will be compressed under this condition. So let us first of all write because lots of things are given to us. So first we are given that it is a monatomic gas. We are having monatomic gas. So which basically means that the value of gamma is equal to 5 by 3 and it is 3 by 2 R, and we are having our Cp will be equal to 5 by 2 upon R. Initial temperature that is our T1 is our 300 Kelvin. Initial volume V1 is our 2.4 into 10 to the power minus 3 meter cube. Cross sectional area of the piston cross sectional area suppose that is of A, it is given as 8 into 10 to the power minus 3 meter square, and the piston displacement let us suppose that is our delta of x, it is given as 0.1 meter. And here the other end of the spring is in the open atmosphere, so there will be atmospheric pressure, that is 1 into 10 to the power 5 Newton per meter square. And we are also given spring constant, K, it is given as 8000 Newton per meter, and we are having atmospheric pressure let us put this given as PA, and that is 1 into 10 to the power 5 Newton per meter square. And it is thermally isolated, so there will be no heat loss, and everything is, you can say, tightly sealed. Okay. And first of all, as initially everything is in equilibrium, therefore we can say that the internal initial gas pressure, that is P1, should be equal to the atmospheric pressure, that is our PA, because everything is in equilibrium. So we can see initial state we are given that spring is relaxed, if the spring is relaxed, we can say that the force because of the spring will be equal to 0, and the piston is in equilibrium, therefore the initial pressure, that is P1, should be equal to our atmospheric pressure, that is PA, and that is equal to 1 into 10 to the power 5 pascals. And from here we are going to find out the number of moles in the gas. For that we can use the ideal gas law. We have our ideal gas law, which is our P1 V1 is equal to NR times T1. We can write our value of N is equal to P1 V1, and we have this as our R times T1. We substitute the value, we get our N is equal to P1 is equal to 1 into 10 to the power 5, V1 is our 2.4 into 10 to the power minus 3, R is our standard, that is 3.14 into T1 is our 300 Kelvin. So number of moles approximately will be equal to 0.09621 moles. Now we can find out the final volume, because the displacement of delta x, so volume is going to change. Okay. So we can say the final volume and for final volume, first of all, let me draw an initial picture. So let us suppose this is the initial position of the piston, and it moves to this new position and this distance is given to us as, we are taken it rather, delta x, and A is the area of the piston that is going to remain same. Okay. And the piston is moving towards right. Therefore, let us suppose this increase in volume is our delta V. So this delta V will be equal to A times delta x. So we can say volume increase that is our delta V is equal to A times delta x. So we substitute the values, we get our delta V is equal to, area is our 8 into 10 to the power minus 3 and delta x is 0.1. This comes as 8 into 10 to the power minus 4. Therefore, the final volume will be equal to V2 is equal to initial volume, that is V1, plus increase in the volume, that is delta V. This comes as 2.4 into 10 to the power minus 3 plus 8 into 10 to the power minus 4. So we get that the final volume V2 will be equal to 3.2 into 10 to the power minus 3 meter cube. Now we come to the final state pressure, because as it expands, this is a fixed position of our rigid support, and to this we have connected a spring. So obviously there will be a compression in the spring in this direction. Okay, and this is our K multiplied by X, that is the force because of the spring force rather. So we can say final state pressure the spring is compressed by 0.1 rather. Spring is compressed and in this case we are going to denote it as X, that is 0.1, especially for our spring purpose. Therefore, spring force is equal to constant multiplied by X. This is our 8000.1 giving us 800 Newton. Now we can find out the pressure due to spring. Pressure due to spring, let us call this as P spring, will be equal to force because of the spring and divided by its area, which comes as 800 divided by 8 10 to the power minus 3. So we get pressure because of the spring will be equal to 1 into 10 to the power 5 pascals. So okay, now we have to, in this case, remember that the spring, let me draw a separate one. So we are having the spring which is compressed, this is rigid wall, and this is the final position. It moved by delta of X. So spring is compressed, so it is going to apply a force in opposite direction, which we called as F spring. And we have atmospheric pressure also, which we called as PA. And from inside, because of the heat supplied, there will be also a pressure. Let us call this as P external. Yeah, external. Okay, we can. let us not call P external, let us call this as P2. So because this is sealed something like this, and this was the initial position of the piston. So externally we are having two pressures, PA and F, this here it is P spring. So under equilibrium condition, this P2 should be equal to summation of our PA as well as P spring. So we can say that in equilibrium condition, under equilibrium, our P2 should be equal to our PA and P spring, and we know both values. We substitute them, we get this as 1 into 10 to the power 5 plus 1 into 10 to the power 5, giving us 2 into 10 to the power 5 pascals. So this is our final state pressure, that is our P2. Now we come to the final temperature. Final temperature, and for that we can use ideal gas law. We can say our P2 V2 is equal to NR times T2. From here we can say our T2 is equal to P2 V2 divided by NR. All the values we know, we simply substitute them. We get our T2 is equal to 2 into 10 to the power 5 multiplied by V2, that is our 3.2 into 10 to the power minus 3. Number of moles we found out is our 0.0962. 0.0926, sorry, 9621 into, and R is our 8.314. So from here we get that our T2 will be approximately equal to 800 Kelvin. So this is our final temperature. Anything else is left? Final temperature and heat supplied. Okay, so we need to find out the heat supplied, that is our Q. So we can say our heat supplied. So we can use our first law of thermodynamics, and we can say our Q is equal to delta U plus work done, and this work done will be by the gas. Okay. And delta U we can calculate. Delta U is equal to our N C delta T, and we substitute the value. N is our 0.09621, and this comes as 3/2 times R. R is our 8.314, and delta is our T2 minus T1, that is our 800 minus 300. So we get that our delta U will be approximately equal to 599.8 joules. Now we come to the work done by the gas. Okay. And as the gas is going to expand, the spring is going to compress. Okay. So basically we can say, as the gas pressure varies, that is a variation in the strength of the spring also. So we can say that the gas pressure varies due to spring. And we can write that the external force will be equal to PA multiplied by A and K times X. And our this X will be equal to our V minus V1 upon A, and external pressure, that is our P external, will be equal to F external divided by A, which comes as our, and this comes as PAA upon A plus this is Kx is our V minus V1 upon A multiplied by A. Here A and A cancel out, so this comes as our PA plus K V minus V1 upon A square. Okay. Now we can find out the work done by the gas as the volume changes from V1 to V2. So you can say work done by gas will be equal to integration V1 to V2, and this is dV, and we can write this as our V1 V2, and we have a PA K V minus V1 upon A square times dV. And we have two terms here, one is PA and this is our KV minus V1, so we separate them, and for the first we are going to get our PA, and this will be our V2 minus V1 plus, and for the second part we can, okay, let us solve it separately because second will be requiring substitution. So for the first part we know that a PA is 1 into 10 to the power 5, and this comes as our 3.2 10 to the power minus 3, 2 into 10 to the power minus 3. So this gives us that our for first, that is our 80 joules. So first part integration is giving us 80 joules. Now we come to the second part. Second part is our K V minus V1 upon A square, and this is our dV, and integration V1 to V2. So in this case let us assume that V1 minus V1 V minus V1 is equal to U. Therefore our dV is equal to our du, and for the limit of integration, as V tends to V1, our U is going to tend to 0, and as our V tends to our V2, our U is V2 minus V1, and V2 minus V1 is our let me write it here. This is V2 minus V1, and we can calculate it. This will be our 3.2 into 10 to the power minus 3 minus 2 into 10 to the power minus 3. So it gives us, one second, this is something is wrong. One second. V2 is 3.2. Yeah, the change in volume is over 8. Okay, and yep, my mistake, I calculated it wrong. Change in volume is 8. Okay, so let me correct this. Change in volume is a V2 minus V1. This is our 8, and 8 into 10 to the power minus 4. Minus 4, 80 joules. Similarly, here also the change in volume is our 80, and this will be coming as 8 into 10 to the power minus 4. Now it's correct. So let us modify our integral. We get this as 0, and this is 8 into 10 to the power minus 4, and we get this as our ku upon a square du, and this will be k upon a square will be our constant. We are left with u square upon 2, so this will be 1 by 2, and u square will be our 8 into 10 to the power minus 4 whole square. So let us substitute the values. Spring constant is given to us as 8000. Area is our 8 into 10 to the power minus 4, 10 to the power minus 3 whole square into 8 into 10 to the power minus 4 whole square. So this comes as our 64. 64 will be our 6.4. So this will be our approximately equal to 40 joules. So we got the second part is equal to 40 joules. So total will be their summation. So you can say that work done by gas will be equal to 80 plus 40 is equal to 120 joules. Now we easily find out the heat supplied. Therefore the heat supplied Q is equal to delta U, which is 599.8 plus 120, which is approximately 720 joules. Next question. It was asked in the year 1989, and it states that for ideal gas, these 4 options are more or less, you can say, standard conditions under which all these processes are going to take place. Okay. And first is the change in internal energy in a constant pressure process from T1 to T2 is equal to NCV T2 minus T1. Okay. And we know that, let us check the option A, and we know that our internal energy U, or we can say our, okay, let me put it, we can say our internal energy U is equal to NCV multiplied by T, and we have to find out the change in internal energy. Therefore, we can say change in internal energy that is our delta U will be equal to U2 minus U1, and we can modify the equation. So we get our delta U is equal to, this is NCV T2 and this is NT1, which gives us NCV T2 minus T1. Okay. And this particular expression, from the equation we can clearly see that this delta of U is only dependent upon N T2 minus T1. So irrespective of any process, that is whether it is isobaric, isochoric or isothermal, the internal energy is only dependent upon the temperature for the ideal gas. Okay. Therefore, we can say that our option A is correct. Option A is correct. Next is that change in internal energy of a gas and work done by the gas are equal in magnitude in the adiabatic process. So in adiabatic process, we know that our Q is equal to 0. If Q is 0, so it means delta U is equal to work done by the gas. Okay. So therefore, this option is also our 2. So these are all standard relationship, and internal energy does not change in the isothermal process. Like we said, that internal energy is only dependent upon the change in temperature. So if isothermal process, the temperature is not going to change, it is constant. So we can say internal energy does not depend. So option C is also correct. And adiabatic process, this also we know that value of Q is equal to 0. So this is also true. So this is basically, you can say, entirely theoretical or based on the basic formulas or basic concept of this. So option A, B, C, D are all true. Next question. It was asked in the year 1990, and it states that an ideal gas having initial pressure P, volume V and temperature T is allowed to expand adiabatically until its volume becomes 5.66 V while its temperature falls to T by 2. So based on this, we have two questions. First, part A, how many degrees of freedom do gas molecules have? Part B, obtain the work done by the gas during the expansion as a function of initial pressure P and volume V. Okay. So initially pressure is P, volume is V and temperature is T. And final, we have adiabatic process. Volume becomes 5.66 initial volume and temperature falls to T by 2. So first is part A, degree of freedom. And we are given it is adiabatic process. So for adiabatic process, we know that the product of temperature volume raised to power gamma minus 1, that is adiabatic index, is equal to constant. Okay. And we know that our this adiabatic index, that is gamma, is the ratio of our constant pressure and constant volume. Okay. Molar heat at constant pressure and molar heat at constant volume. And between the two, we also know the relationship that constant volume constant pressure molar heat is equal to constant volume molar heat plus R. And so we can also write that our gamma is equal to 1 plus R divided by constant volume molar heat. Okay. And we know that the degree of freedom that is our F, sorry, yeah, we can write other ways also. Degree of freedom F is equal to twice molar heat at constant volume divided by R. Most you can say the easier one is our constant volume molar heat is equal to F upon 2 times R. Okay, so we can just reverse it. And at constant volume, we know that the degree of each degree of freedom contributes R by 2 to the specific heat at constant volume. That is a standard, you can say, terminology that is used. So from here we can say that each degree of freedom contributes R by 2 to the heat capacity at constant volume. At constant volume. Thus, we can write that our gamma is equal to 1 plus R, and in place of this our CV, we can write F by 2 times R, and this comes as our 1 plus 2 upon F. And by making slight adjustment, we can say our F is equal to 2 upon gamma minus 1. Okay. And we have to keep in mind that the process is our adiabatic. Okay. So we have to calculate this our gamma for adiabatic condition, and we have that our initial volume V1 is given as V and temperature is our T, and our final our volume V2 is our 5.66 times V, and our final temperature, that is T2, is T divided by 2. So we can use the adiabatic relationship, which gives us that our T1 V1 gamma minus 1 is equal to T2 V2 gamma minus 1. And we substitute the initial and final conditions. We get this as TV gamma minus 1 is equal to our T by 2, and this comes as 5.66 times V, and we have this as gamma minus 1. So T we can just cancel out throughout. We are left with our V. So we get this as V gamma minus 1 is equal to, we can write this as our 5.66 gamma minus 1 V raised power V raised power gamma minus 1 divided by 2, and this gamma minus 1, this also we can just balance it out, and from here we get our 2 is equal to 5.66 gamma minus 1, and we can just take our log term and we get our log of 2, natural log of 2 is equal to gamma minus 1 natural log of 5.66. So we can say that our gamma minus 1 is equal to natural log of 2, and this comes as our natural log of 5.66, which will be coming as 0.4. Therefore our gamma is equal to 1 plus 0.4, giving us 1.4. So we got the value of gamma. Now we can just find out degree of freedom. That is our F is equal to 2 upon gamma minus 1, that is 1.4 minus 1, approximately that will equal to about 5. Okay, so we can, from here we can also say that value of F is equal to about 5. Therefore we are going to have degree of freedom of 3 for our translational, and for 2 our rotational. We come to the part B, that is our work done. Work done by the gas during expansion. Process is adiabatic. Which means that Q is equal to 0. If Q is equal to 0, we can write that our delta of U, which is our Q minus work done by gas, which will be equal to negative of W of our gas. And delta U we can easily find out. We know that our internal energy, our U, is equal to N constant volume heat, that is multiplied by T, and we know that this is CV is equal to F upon 2 times R, and we have value of F is over 5, so this comes as over 5 upon 2 times R. So change in internal energy, that is our delta U, is equal to N CV T2 minus T1. This comes as our N 5 by 2 multiplied by R T by 2 minus T, and this comes as our minus 514 nRT. Therefore we can see that the work done by the gas will be equal to, that is minus of delta U will be equal to minus of minus 5 by 4 nRT, which comes as 5 by 4 nRT, we are supposed to do it in terms of pressure and volume, so we can use PV is equal to nRT. So we know that PV is equal to nRT. So we can say work done by gas is equal to 5/4 times pressure multiplied by volume. So this completes the 4 questions, and we did for 1990 1 question, 1989 2 questions, and 1988 1 question. So this completes all the 4 questions. Thank you.